So hi everyone, I'm Kabir. I'm a fourth-year PhD student at UIUC. I work with my advisor Dakshita Khurana, and this is going to be my talk on the cryptographic foundations of interactive quantum advantage. This is my recent paper at Stock and QIP this year, and is based on joint work with Mark Zandri. And please interrupt me, ask questions, try make it like as interactive as you want, be as like rude and stop me and say, no, please go back and ask questions, because giving online talks otherwise I find it very like dry, almost boring. It's much more fun and interesting. And I'm more enthusiastic if people like ask questions so I know what parts you're understanding, what parts you're not understanding. So let's start. And the first thing I want to start off by noting is that one of the central goals of quantum computing research, if not like the central goal, is to understand quantum advantage, which is to say, when can quantum computers actually do something that classical computers cannot, or well, efficient classical computers cannot. And really, we want to not just understand, but we also want to demonstrate quantum advantage, which means we want our quantum advantage to be efficiently verifiable. No point doing something if like you can't even tell that you've done it. So there are several approaches to this idea of verifiable quantum advantage, but I want to take a particular perspective and I want to divide it into two categories. So the first category is what I will call non-interactive quantum advantage, where just there's a classical verifier, there is a quantum prover. The classical verifier is just going to send over some hard NP problem. Quantum prover is going to solve this problem and send over the solution. The solution is just a classical string. The problem is just a classical string problem. And here, no classical prover could have solved the problem, and the quantum computer solves the problem. So you know, okay, this is a quantum computer. This has some quantum advantage. And this encompasses most of the common forms, like Shor's algorithm for factoring. You send like some big prime number, it factors it and sends it back to you. Things like DQI, some proposals for these verifiable sampling based advantage, Yamakava's Andrews protocol. All of these are like this send challenge, get response type of quantum advantage. But there's actually a second other form of, or actually no, here one thing I wanted to say, implicit in all of this is this underlying assumption that there exist these kinds of problems, that there exist these problems which are in BQP, so quantum computers can solve them. And they're in NP, which means classical verifiers can check that the solution is valid, but they are hard for classical provers, classical algorithms to solve. So implicitly, there's this assumption of hardness for this class of languages. And there is, however, the second type of quant. Yes.
Oh, sorry. You just want to like mention. So like just to clarify, apart from like we can show like unconditionally in the random oracle, you have this advantage. No?
Yes, but the random oracle gives you this kind of problem. Like relative to the random oracle, this problem exists unconditionally. But there is still this kind of hardness that, well, you can think of random oracle as an assumption. You can think of it as just in this oracle model, you don't need assumptions. But like, then you can say we can build cryptography without any assumptions as long as you have a random oracle. It's like, okay.
I agree. I think that to me somehow like the random oracle and the existence of BQP intersect NP problems. They are maybe slightly different. Yeah, but that's all. Yeah.
Sure. Maybe the formal statement I'd say is relative to the random oracle, Yamakava's Andrews show that there exist average case hard problems in BQP to the O intersect NP to the O. Sure.
Thank you.
So what our paper is actually about, though, is about the second type of quantum advantage, which is not this kind of algorithmic send a problem, get a solution. It is an interactive form of quantum advantage where there's a classical verifier, quantum prover. They send many messages back and forth. And at the end, the receiver either accepts or rejects. And this type of interactive quantum advantage was first proposed in the BCM plus BCM VV18. This is the famous Mahadev protocol, also is sometimes called. And here, instead of like assuming this explicit separation, that there's some language it is in BQP, not in BPP, so we are kind of assuming this gap between what quantum and classical can do. Here, in your assumption, at least, there is no such gap. All you assume is some cryptographic primitives are secure. These can be like trapdoor claw-free functions or even like trapdoor permutations, things like that. You just assume that they're secure. Nothing about like whether quantum can break and classical cannot. Just assume security. And the thing to note here is, again, because non-interactive quantum advantage explicitly has this separation, it explicitly implies that BQP is not equal to BPP. However, the interesting thing, this interactive form of quantum advantage relative to some oracle can exist even if BQP equals BPP. So even if there is no advantage in algorithms, there's still some kind of advantage that persists just because of this quantumness in the interactive setting. And okay, like maybe this, depending on how familiar you are with this literature, this isn't that remarkable, that new. This work has been out for Mahathir's protocol has been out for many years. But when I first learned about this just like blew my mind. That okay, we are saying that even no advantage in standard computation. Every like language you can solve even with BPP. There's still this kind of advantage which persists specifically in the interactive setting. There's something about interaction that is allowing us to get quantum advantage. So the goal of our paper is to understand the foundations of this kind of interactive quantum advantage. And just a heads up, I will be using the term proof of quantumness interchangeably with what just verifiable quantum advantage, the way I defined it. So proof of quantumness just means this. There are, in other contexts, people use it slightly differently, but for this talk, proof of quantumness, verifiable quantum advantage. So the goal is to understand the foundations of interactive proofs of quantumness. And why should you care? Like, I think this problem is interesting in itself, but okay, here's some connections to other things, some motivation. Well, first of all, it is a major research area to try to understand and minimize the kinds of assumptions required to construct these proofs of quantumness. So earlier started with very structured assumptions and slowly reducing the structure, trying to make it as simple as possible. Maybe you can even run it on a computer one day. But in order to minimize the kinds of hardness assumptions you are making, you should at least understand what kinds of hardness assumptions are fundamentally required and what things are maybe superfluous and you can hope to like remove them in future work. Another reason, proofs of quantumness, or rather the existing constructions that we have for these interactive proofs of quantumness, are deeply connected to all kinds of different quantum crypto primitives. And two particular aspects that I will highlight here. First is the round complexity of these underlying proofs of quantumness. They usually carry over to the many applications of these kinds of ideas. So the application of things like classically verifying quantum computation, quantum fully homomorphic encryption, remote state preparation, certified randomness. The ones I'm most interested is like classically verifiable proof systems for QMA, or even just like in general proof systems for QMA, which may have like some zero knowledge property or something like that. And in that setting, there is a second problem from proofs of quantumness which carries over, which is that the existing proofs of quantumness or the techniques we have, they tend to be private coin. So the verifier's messages need to have some structure. And this lack of a public coin way of doing proofs of quantumness is a major barrier in achieving publicly verifiable NISICs for QMA. So like non-interactive zero knowledge proofs for QMA, which is a pretty major open problem. If we just had a public coin way of doing Mahathir's protocol, it would just be solved. You just fiat Shamir it and then you're done. So understanding proofs of quantumness should help us better understand all these applications. What are the limitations? What is fundamental? And so on.
Kabir,
So,
a couple of
yes.
questions, or I can ask them after you.
No, please ask right
now. Okay, so first, are there any complexity theoretic barriers to proofs of quantumness? Can we have proofs of quantumness without any assumptions at all? Let's say we allow polynomially many rounds. So
yes.
That was the first, and second was Yamakawa's entry was public coin, but that was in the random oracle model. Can we hope to have public coin, let's say, based on knowledge assumptions or some exotic assumptions?
So This will emerge more as we go into the talk, but I am trying to draw a distinction between the kinds of advantage which come from interaction and the kinds which come from just some algorithmic problem. And it seems like the kind you need, or the kind that the techniques that we are using to solve in all of these applications are coming from the interactive view. You can get a non-interactive proof of quantumness in the public coin by, for example, using a random string to sample a prime number. So you just sample a random string. This is going to map to some prime number, and then say, okay, not prime number, obviously, to some number, and then ask it to factorize. So you can get like public coin, but it's going to be the non-interactive kind and not the interactive kind. So right now, this distinction is a bit like blurry. Like, what do you mean interactive? And part of our results is like convincing you, hopefully, that this distinction is real and can be made formal, that there's something very different going on in both of these worlds. But yeah, so I don't know about knowledge assumptions and things like that. I haven't thought about it at all. I don't know that much about knowledge assumptions. Possibly they can be used to bypass some of the barriers we show, but maybe it will come up and we can look at it again.
Sure. And is there any evidence that we need assumptions at all for proofs of quantumness?
Yeah, right. So again, this will show up later, but we know that a proof of quantumness implies BPP is not equal to sharp P. Because like, or say P space. If BPP is P space, any interactive protocol you can just simulate. But they are like slightly, so you can say something slightly stronger. And I'll get to it.
Thank you.
Right, and the third thing is like my main reason, which is that, it is this interactive setting that is fundamental in complexity in cryptography, and we should just study and try to understand all kinds of quantum advantage. Like, this is a very natural form, and given that it is not captured at all by the question of BQP versus BPP, that it is something different, that we should seek a deeper understanding of it. And I want to add, this is not like some artifact of like some kind of weird crypto thing. This is a meaningful kind of advantage. Like, you can construct cryptographic schemes where all your underlying assumptions are secure against a quantum attack. And against classical adversaries, the scheme is secure, but against quantum adversaries, the scheme still breaks. Even though you built everything from LWE, like your commitment scheme or whatever, is insecure against quantum attack because it has interaction in it, or its security definition involves some interactive game. So it is a meaningful form, and we should seek a deeper understanding of it.
Sorry, can I interrupt you with one more question?
Yes.
About the previous slide. So when you're saying that this connection with like all these primitives,
Yes.
I'm guessing it doesn't necessarily imply that all the lower bounds you establish for POQ,
No.
let's say in terms of number of rounds, should also carry the right, because we don't have any typical black box construction that goes from POQ to those, right?
Yes.
Okay, so when you say connection, you just mean that the constructions are similar, or
it's a model connection more than a. It's more that all the techniques that we know so far are building off of Mahadev's protocol and similar ideas. And part of why, like, generically proof of quantumness hasn't been known to give these is because of this. Because of, in my view at least, because of the definition of proof of quantumness includes both non-interactive and interactive. And this is coming, I believe, that all of these applications are much more linked to the fundamentally interactive kind of proof of quantumness. But
I see. So
nothing here is
like
formal. This is, sorry?
I see. No, I just want to like understand your intuition. If you would expect that maybe for some of these other applications, those bounds should potentially also be true. I see.
I think it is a very interesting problem to try to study whether techniques from here can apply there.
Yeah.
Whether you can use ideas, what more is needed.
I see.
But yeah,
okay.
As it stands, it is more of a limitations on current techniques rather than limitations on these applications themselves. Or maybe you can see it this way. Some new breakthrough in proofs of quantumness would probably help us solve these other problems better.
Right. Okay, sounds good. Thanks a lot.
Right. So what is known so far? Well, trapdoor-claw-free functions imply 4 message proofs of quantumness, and with a bunch of other bunch of other crypto primitives you can like get various forms. So with IO and LWE, you get 4-message public coin-ish asterisk there, but public coin proof of quantumness. Really, the later messages are unstructured, but the first message still has to be structured. But from trapdoor permutations, we know that if you don't care about round complexity at all, you can get like some polynomial message proof of quantumness where you have many, many rounds. And the main takeaway here is that these are all like reasonably structured assumptions. They have these trapdoors, and you need IO or this claw-freeness structural property. What about like lower bounds? Do we know that this structure is required? Well, here the picture is much murkier because we know that proofs of quantumness, like trivially with the complexity theoretic way, imply very mild separation, which is BPP does not contain PP, or PP or sharp P, morally the same thing. And this is almost trivial. And we can say something a bit stronger. So this is actually a major recent result by Morima, Shirakawa, Yamakawa, which shows that proofs of quantumness imply something called the classically secure one-way puzzle. So this is a quantum crypto primitive. You need a quantum computer to generate it, but security only holds against classical adversaries. And the thing I want to highlight is there's a big gulf here between the kinds of assumptions we seem to need when we are building all of these and the kinds of assumptions we can show that are required, because these are like really weak. In fact, under certain conjectures, you can show that these are actually equivalent to PP not in BPP. So even though it takes like a good deal of work to get this like slightly stronger lower bound, it's unclear whether it's like actually stronger in a very meaningful way. So what's going on here? The things you're getting are really weak. They don't even imply P not equal to NP, while the stuff you're using is all this fairly heavy-duty crypto. So why is there such a large gulf? Well, one reason is that the existing techniques have not taken advantage of efficient verification at all. So they're like, okay, we don't care if the verifier is efficient or not. We're just building it. So something should come from there. But in my mind, there is a second, much more fundamental reason for why there is this gulf. That reason is as following. So I hinted at this earlier, but like non-interactive proofs of quantumness, these are basically the same as average case hardness of BQP intersect NP. So here there's no cryptographic assumption, but we are assuming an explicit separation between BQP and BPP. Likewise, interactive proofs of quantumness we get from these various crypto assumptions. And both of these fall under the same heading of proof of quantumness. And like you can take a non-interactive one, add in some dummy rounds, and hey, it's now interactive. It's not very clear how to distinguish between these two types. So they all fall under the definition of proof of quantumness. And this is a problem because if you say tomorrow come up with some new lower bound for proofs of quantumness, say proofs of quantumness imply P not equal to NP, or imply one-way functions, let's say. So this lower bound would have to be implied first by all of these crypto assumptions that give you interactive proofs of quantumness. But also, separately and independently, the same lower bound has to be implied just from average case hardness of BQP intersect NP. So on the right-hand side, there is no explicit BQP not equal to BPP statement, but there is some crypto assumptions. On the left-hand side, there is no crypto, just average case hardness, but there is an explicit separation. So these two assumptions are very different in flavor. They seem kind of uncomparable. They're saying very different things. But whatever lower bound you have has to be implied by both of them separately. What this means is any lower bound you get will not be able to really capture the underlying hardness, either of interactive proofs of quantumness or of non-interactive proofs of quantumness. In a sense, you're trying to do too much. It will have to be very weak. And this brings us to like one of the theses of the paper, which is to make progress on this problem, we must disentangle this fundamentally interactive proof of quantumness from this non-interactive, or what we sometimes call trivial proofs of quantumness. So how can we do something like this? Well, our first result shows one way to start thinking about this and showing that these two are actually distinct types. And the result is basically saying a proof of quantumness is either trivial or non-interactive, or it is fundamentally cryptographic in nature. And this only holds for constant rounds, small caveat. But suppose you have a constant round proof of quantumness, then we say that either you can round collapse it. So you can just make it 2 round. So it was really just non-interactive in disguise. You can just strip away these extra rounds. Or it must imply fundamentally the existence of some kind of cryptography. So it has to be cryptographic in nature. And formally what...
Sorry. I was just going to ask what you meant by it would imply cryptography. I'm guessing some primitive in some sense. Okay, which are
yes.
Sorry.
So formally, we get that constant round proofs of quantumness imply either non-interactive proofs of quantumness or a variant of one-way functions or a variant of public key quantum money. A public key quantum money is this like heavy-duty primitive. So really, in my mind, this is saying one-way functions, but technically these two are not strictly comparable. And the variant is because of things like a infinitely often auxiliary input. When you do these kind of win-win results, you often get these extra adjectives, which make it a little less clean. But morally, what it is saying is you need like one-way functions or some kind of quantum unclonability, or you're just non-interactive and you have padded the round somehow. So I will not get too much into the technical details of how we show this. It's I would encourage you to look at the paper. It's not a very long proof at all. So, but really, what I want to use this result as is a kind of jumping off point. How can we now start to capture this interactive quantum advantage? And this gives us the first hint, which is it is these kinds of proofs of quantumness are fundamentally cryptographic. And therefore, if you think cryptographically, we can try to capture the hardness using the standard paradigm for building cryptographic constructions. And this paradigm will actually be sensitive to the difference between interactive and non-interactive. And what do I mean by that? Well, all known interactive proofs of quantumness, and in fact, the vast majority of all cryptographic constructions are proven secure via black box reduction. What that means is when you give your construction in your paper, you will give an efficient algorithm R, and you will say that there's some assumption C. So assumption C is going to be something like LWE, one-way function, some kind of hardness assumption. And what you'll show is, here's my proof of quantumness. For any classical algorithm A, if the classical algorithm can convince the verifier to accept with better than 1/3 probability, then R, the reduction, can use A to break the underlying assumption C. So given any adversary which breaks my interactive proof, I can use this adversary to break one-way functions or something like that. And the crucial thing here is that this reduction is black box, which is to say it works. It only uses the input-output behavior of the adversary, which means it does not care about how the internals work. In particular, it does not care about the runtime of the adversary. For any classical algorithm, it has to use this algorithm to break the underlying assumption C.
And
now,
it can also rewind the adversary.
Yeah. It can rewind, it can do like all the standard things that black box reductions can do.
Right. And this class of assumptions, is it like the falsifiable assumptions, or what is this? So what class of assumptions are you working with?
So C is going to be falsifiable assumptions, but even inefficiently falsifiable assumptions. So things like IO are fine, or even like P not equal to sharp P or things very, very broad, but like I think knowledge assumptions would not fall in this category, right?
Yeah.
So
knowledge assumptions do not.
Yeah, and things like random oracle is not a Basically, if
Right.
there is a security game for the assumption, even if the challenger for that game has to be inefficient.
And can the assumption, for instance, be some sort of an interactive assumption?
Yes. Yes.
Okay.
R, A, and C can play some interactive game.
Right. Okay. Yeah. Thank you.
Yeah. And so just to complete the exposition, why is this the way we do it? Well, because suppose you have proven there exists this reduction R that has these properties, then you can show that no classical adversary exists. This is because if I gave you a classical adversary which was efficient and broke this game, then R to the A is now overall an efficient algorithm which breaks your assumption C. And your assumption C is going to therefore because you believe your assumption holds, there's no adversary which is no efficient adversary can break the assumption. This means that no such efficient A can exist. Now, an inefficient A can exist. An inefficient A unbounded time can obviously exist. It can break your proof of quantumness. But then when you plug it in, R to the A is not efficient. So even though R to the A will break your assumption, that's probably fine. So in unbounded time, you can break the assumption. That's usually the case. Okay, so now with this background, we can state our results for our bounds on a slightly limited set of proofs of quantumness that still nonetheless capture all known constructions so far. So first, let's define what I mean by black box proof of quantumness. Black box proof of quantumness is a proof of quantumness that is proven secure via black box reduction to a post-quantum assumption. Now, why post-quantum assumption? Well, if your assumption itself is secure only against classical adversaries and not secure against quantum adversaries, you have in some sense already assumed this the separation between classical and quantum. So in a sense, your assumption itself is already a proof of quantumness. So we want to avoid that. We want to really be capturing things that are coming just from advantage and not from already assuming a separation. So some assumption which is secure against quantum attack. Therefore, we get the following results for these kinds of proofs of quantumness. So first of all, for 3 messages. Well, for 3 messages, we show that this is straight up impossible. You cannot have 3 messages. You need at least 4 messages, which means in particular that existing constructions are tight. The Mahadev protocol uses 4 messages. And any interactive form of proof of quantumness needs at least 4 messages if you're doing it via black box reduction to cryptography. Next, more than 3 messages
sorry,
for any.
Just a quick question. So for 3 messages, does it matter who sends the first one? Or maybe, okay, so if the challenger.
Right. So if the verifier sends the last message, that is kind of meaningless because the verifier's response doesn't
Makes
depend
sense.
on the message sent.
Yeah,
So
yeah.
we always assume the prover is sending the last message. And then this induces whatever structure you want.
Got it. Thanks.
Right. So second thing, for constant many messages, here we show and what is in crypto literature called an oracle separation. So we show that you cannot build it from even extremely powerful cryptographic assumptions like indistinguishability obfuscation. And indistinguishability obfuscation can construct almost everything in classical cryptography. Like even most of the exotic primitives in quantum cryptography, we only know how to construct using indistinguishability obfuscation. There are very few things we know that you cannot construct with IO. These are things like things that revolve around collision resistance and like statistically hiding commitments. Those are the two, and they're fairly related, the two big exceptions. And well, here's a third exception. Constant message proof of quantumness. You can't build from IO. Morally, to me, this is saying that you need some form of collision resistance. So existing constant round constructions do have like claw freeness, which is a form of collision resistance. So there's a function for which it's hard to find x1, x2, which both map to the same value. But I would like to make that formal, but that is just my interpretation of this result. Really, all it is saying is you cannot build it from IO plus one-way functions. So we're not saying it needs collision resistance, but if you don't have collision resistance, basically any other property that we've thought of doesn't give it, because it can be built from IO. Finally, for polynomial messages, we show. For the polynomial setting, actually very tricky to work with. One reason for this is we have no information theoretic lower bounds that say that you cannot verify quantum computation in polynomially many rounds. So there could exist just an information theoretic protocol to verify all quantum computation with a classical verifier in polynomially many rounds. And in that case, getting a proof of quantumness is really easy. You just have some hard problem that BQP can solve. It doesn't even need to be verifiable. You just plug it into your verification thing, and at the end, your verifier is you're going to be able to verify it. So if that example wasn't clear, sorry, I was like ad-libbing, but the polynomial round setting is very tricky to work with. But even here, we get a slightly improved result, which is that with polynomial messages, this requires quantum secure one-way puzzles. I've not explained what a one-way puzzle is, but the main thing you need to remember is earlier we know that proofs of quantumness require classically secure one-way puzzles. So here we've upgraded the security to be against quantum attack. And this makes a big difference because unlike classically secure one-way puzzles, which don't have any like crypto application, quantum secure one-way puzzles can be used to get like quantum commitments and MPC and zero knowledge with quantum communication. So you can actually get a lot of useful crypto from quantum secure one-way puzzles, which we don't know how to get from classically secure one-way puzzles. Okay, so any questions at this point? Yeah, one remark I want to add. All of these above also apply when we allow the verifier to be unbounded. So we don't put any, here we are not using efficiency of the verifier. So even for an unbounded verifier, sorry.
No, so just want to clarify. So what are some known constructions of like quantum secure one-way puzzles? Like what do they rely on? Just to maybe at least compare it to like the trapdoor permutation construction of poly many
Right.
POQ.
So quantum secure one-way puzzles, we think like I have a paper where we construct quantum secure one-way puzzles from worst case quantum hardness of sharp P. So just sharp P not equal to BQP, and some conjectures from the quantum advantage literature. So it's murky what the picture is, but something more in the sharp P hardness land instead of NP hardness land. But still more than the trivial. The trivial thing is more like classical computers cannot solve sharp P. And here it's quantum computers cannot solve sharp P, plus some similar conjectures. The main thing here is not that, oh, there's some massive improvement over classically secure one-way puzzles. It's just that you actually need crypto, not just this classical secure object, which has this weird asymmetry between you need the quantum construction to construct it, but your adversary can only be classical, which is not useful for crypto as far as I know.
Kabir, sorry, this might be a silly question. So here, when you talk
Right.
about black box reduction, do we care whether the reduction is classical or quantum? Does it have?
No. So all of these work for quantum reductions as well.
Mhm. Thank you.
Yeah, this is a good question to ask. Like later on, I have some results which only work for classical reductions, but these at least no restriction on the reduction. Okay, so let's look into, but not really the full result, but the basic idea that all of these or most of these are stemming from. And that is this idea of this paradigm of meta reductions, which is so recall that we have this algorithm, this reduction R. It takes any classical algorithm, uses it to break the assumption, and any classical algorithm breaking the proof of quantumness, the reduction will work with. However, also recall, because this is a proof of quantumness, the honest quantum prover does have to succeed, right? So there does exist an efficient quantum algorithm Q, such that if Q can make the Q can make the verifier acceptable better than 2/3. So the question is, R can somehow use any classical A to break the assumption, but it stops working when Q is quantum. R is not able to use Q to break the assumption. So R, in some sense, finds out that, oh, Q is quantum, And that is how we show that it is secure. But how possibly can it do this? Because it is only interacting with the input-output functionality. It is not looking at the internals at all. All the inputs and outputs are just classical messages. So how does it know that no, you're actually quantum, you're not classical? And
sorry, just a quick question, Kabir. So here, for instance, you mentioned that you can you allow rewinding, right? In this reduction. So for example, that would be one way where the thing won't work, right?
Yes, my next slide has heading rewinding. So
okay,
audience is too fast for me. Yes, you are correct that really, even though it is technically just interacting with the input-output functionality, that means different things when your algorithm is classical and when that is quantum. In particular, here is the standard technique by which all of these proofs of quantumness are usually shown secure. And this is a technique called rewinding, which works as follows. So R is going to try to use an adversary to break the assumption C. And the way it does it is going to try to obtain two transcripts of the protocol. So first, R is going to run the protocol once, send message M1, receive message M2, send message M3, receive message M4, and finally obtain this transcript tau, which is M1, M2, M3, M4. This is one run of the protocol. Next, it is going to start this protocol again, send the same first message, and then receive the same second message. So assume the adversary, the classical adversary, is deterministic. We can do this without loss of generality. If you disagree, then I can convince you. But for now, assume A is deterministic. So you send M1, you get the same message M2. So far your transcript looks the same, but then you send a different M3, and therefore you get a different M4. And now, given these two transcripts, which are same in the first half but different in the second half, now you can use this to break your assumption C. So what goes wrong if you have a classic quantum prover? Why can't you get these two transcripts from a quantum prover? Well, you can send M1, and generically, like what is a quantum prover doing? What does it mean to be a quantum prover? Well, it will apply some measurement, which depends on this message M1 to its initial state, and it will obtain this measurement result M2 and this residual state phi M1 M2. Then it is going to send over M2, R is going to send M3, and now again, to obtain the fourth message, you will apply a measurement, which depends on the whole transcript so far, and you'll apply that measurement to the internal state, the leftover residual state, phi M1 M2. And you will apply this measurement and obtain M4 and send over M4. So R can use this quantum prover to get M1, M2, M3, M4 using these measurements. Now what happens if R tries to get the second transcript? Well, when R sends M1, the first measurement is, because it's a measurement, it's just going to return some like M2 prime. It's different. So it's like, oh, I can't even get M2 prime. I can't even get like the same M2. Okay, this is less of a problem in my mind, because like M2 is not the thing you need. Like you can just like say, okay, I know you're supposed to be sending me M2. Really what I care is what you send me after M2. So just pretend like I got M2 last time, this time also I'll just pretend I got M2. Now I'm going to ask for a different M3. But this is where like this pretending catches up to us, because to get a different message M4, Q normally would be applying a measurement to its internal state, phi M1, M2. And how would it obtain phi M1, M2? By performing this first measurement. But now, because it has to, like if it performs this measurement again, it will get a different M2 prime. It will not get phi M1, M2. It cannot obtain this state, and it cannot even obtain phi M1, M2, and is not able to answer with a new fourth message that is consistent with M1, M2. So basically, R is detecting or checking that Q is quantum by doing this rewinding, because if it was classical, it would be able to obtain these two transcripts. But with the quantum prover, it is not able to get these two transcripts. And without these two transcripts, it can't break the underlying assumption. But this also means that R now knows that you're quantum. Is this part clear? Like I've had in the past many questions about this, because this, for me, it seems very like obvious because I do crypto. But for many like complexity people, this was very new to them. Any questions at this point? I'll just take a
I
sip
just
of
wanted to ask one thing. You mentioned that the reduction itself could be quantum, and that is okay,
Yes.
right?
So here I'm just assuming that R is classical for exposition's sake. I will say a little bit more about what happens when R is quantum, but yes, we can handle that case. It is like more involved.
Right.
Okay. So here is a very interesting consequence of this fact. So R is failing to obtain these transcripts, and in fact, it must fail to obtain these two transcripts, because if it does obtain these two transcripts, well, not two, maybe it needs n, but for now, imagine you just need two. If it ever obtains these two transcripts, it can break the underlying assumption. What this means is, by the security of that assumption, this internal state phi m1, m2 must be hard to clone. And what do I mean by that? So you may have seen like BB84 states. Those are also like hard to clone. But those are hard to clone because the state itself is not information theoretically defined from the information you have been given. Here, the state phi m1, m2, suppose you sent m1, received m2, the state is exactly defined. The algorithm Q on an information theoretic level exactly defines what the state phi m1, m2 is going to be. The hardness here is purely computational. That given phi m1, m2, you cannot produce two copies of phi m1, m2. And why is this the case? Suppose this cloning was easy. Then R could do a different strategy. It could come up with a different algorithm, Q star, and use Q star in a clever way to try to break the underlying assumption, which is Q star is going to proceed as normal, except when it gets to the stage where you're answering M3, it is going to make clones of phi m1, m2 to get many copies of the state phi m1, m2. Now in the future, when you try to get your second transcript, you recover M2 as before, and now Q star is going to say, hey, for M1, I gave you M2, so in order to get my fourth message, M4 prime, I'm just going to use one of the clones that I already made. So recall, the problem was constructing the state phi M1, M2 again from scratch. Now you have a bunch of these copies. You can just use one and measure to get M4 prime. So if you could make clones of this state, like exact clones, or maybe up to some small statistical distance, it's fine. If you could make clones of this state, then you would be able to obtain these transcripts. You'd be breaking the assumption. Therefore, making clones must be computationally hard. Because if it was easy, we can effectively rewind, and RQ star will break the assumption. And this basic idea that this state has to be hard to clone is what enables us to get our results. So for three messages, note that the equivalent for the state phi m1, m2 is just going to be phi m1. In particular, it doesn't.
Sorry, sir, before you go on, just probably a dumb question because I didn't. Okay, I'll just ask anyway. So if you have, does it matter what the length of these messages is? Run into something being exponential, so it doesn't occur often enough. Sort of issue.
Yeah, I guess that has to be the case. As in, okay, not for cloning. If you can clone, then everything is fine. You can just rewind. But the thing that you are pointing out is, suppose M2 was just 1 bit. Then I guess then it is not possible to have a state that is hard to clone if you're getting the state by just measuring 1 bit, because you just measure it again and again and you are going to hit that same state. Or that state is such low probability that you're not even going to hit it in the honest execution.
Yeah.
So yeah, that is a good point. So it does say something about message length. I have not looked at that angle at all.
Okay, thanks.
Yeah, interesting. Yeah, for 3 messages, if your proof of quantumness was just 3 messages, then the state that you have, it doesn't really depend on anything sent by the reduction or by the verifier. It is just the output of your after you do your first message on just get 0. In particular, even before the protocol begins, Q can just like sample some M1 And now Q knows exactly what its internal state is. It has a copy of it, and also, at least information theoretically, that state is fully defined. So what you can do is you can now construct a Q star, which simply receives many copies of this state as advice. It just has hard-coded the first message and gets many copies of the remaining state just as advice. And now you don't even need to clone any state computationally. You just have copies and you break your underlying assumption. Now, one question people ask at this point. What if I only want my protocol to be secure against uniform adversaries? But okay, with advice you can break it, but okay, I only care about uniform security. I'm saying that doesn't save you at all. What I'm saying here is whatever your underlying assumption is, say your assumption is LWE. I'm not saying that your proof of quantumness has to be secure against uniform adversaries. What I'm saying is your underlying assumption is explicitly broken against an attack that has advice. So you get this particular set of states as advice. You take your reduction R, you run this attack, and it will break your underlying assumption. So it will break LWE if you ever construct a 3-message proof of quantumness using this black box technique. So unless you believe LWE itself is broken against non-uniform attack, which would be like a big result if you could show this. But unless you believe that you can't use black box methods. And I'm not explaining it here, but extending this, you can get like for 4 messages or even like multiple messages, polynomially many messages. From prior work, we've shown that this hardness of cloning states, which is a vague term, but here it means cloning states exactly. This implies quantum secure one-way puzzles, and that is how we get our one-way puzzle result. The oracle separation is fairly involved. I'm not going to get into this, but that shows something for constant rounds, and that uses some different ideas. Right.
So here, if the state is sorry, just to quickly check. So if the advice is not exactly this, even then I suppose the result would be more or less true, right? Or there's something, is it like very sensitive to noise is what I'm trying to understand?
No. It's not noise sensitive. Yeah, basically if you have the state with some noise, your success probability goes down a bit, but like as long as the noise is not too much.
Got it.
Yeah.
Thanks.
Yeah. But what I mean by cloning states exactly, maybe that is the thing which tripped you.
Yeah. Mm-hmm.
For example, quantum money setting, we often talk about cloning a state, but it means that I've given you a state and I have a verifier. And this verifier is going to say what a valid state is and what an invalid state is. You can now, and the thing you want to stop is cloning this money state, where cloning could mean coming up with a state which is completely different, completely orthogonal to this original state. Yeah, but still makes a verifier accept. So here we are not saying clone with respect to a verifier. We are saying clone with respect to trace distance. So trace distance has to be reasonable. Can't be like close to 1.
And what if it's computationally indistinguishable somehow? Does that, like, I don't know, BQP couldn't distinguish it? Does it not say anything in that case?
So in that case, so the problem is that if I give you many copies of a state, and then I might ask is to produce a computationally indistinguishable version of that state, and you have those copies, you can just check. Like then it becomes synonymous with statistical distance. By a swap test, you can just check whether you're giving exactly that state.
Got it.
Yeah. So it's like, again, maybe there is a way. Like if all your copies are computationally indistinguishable, probably it still works. But like, I mean, yeah, sure. It's just you need to define carefully and not thought about it.
Yeah. No, I agree.
Okay. So far, all the techniques I've talked about are just I've assumed the reduction is classical. I've been sending these nice message M1, message M2, and then you start a clean new run. What happens if your reduction is quantum? Well, when you're running a quantum reduction, recall this reduction only works for classical adversaries. So inside the proof, ultimately what you'll be saying is, look, this Q star, it looks just like some classical adversary. So we know that our reduction is going to work. It's indistinguishable from some unbounded classical adversary. However, when R is quantum, R has like another way of telling if your algorithm is doing something quantum or not, and that is by making quantum superposition queries. And for our Q star, as naively described, to work, it must record what messages R is asking. In particular, it has to, when you say M1 and get M2, later on you're going to send M1 again. And Q star has to remember, oh, I already answered this one. The answer is M2. And for future messages, I need to go to my database and look up what is that internal state that I've already made copies of and take one of those. So it needs to remember what was queried before so that it can do the bookkeeping required to maintain its clones. That, okay, this is the state that I had many copies of. That this is the one I need to retrieve. So it needs to remember what are queries. With classical queries, this is very easy. Just write it down. This is fine. With quantum queries, this becomes like a fairly known major problem, because what ends up happening is if you record too much, I think my camera is blurry for some reason. Yeah, if you record too much, you end up entangled with your quantum reduction. And that the reduction get detected, because no classical algorithm should ever be entangled with a quantum algorithm. It should just be some input-output functionality. So how do you solve this problem? How do you record while still looking completely like your classical? This is again, this problem has arisen before and has been solved before by the compressed oracle technique by Mark. And you would think, okay, let's just try to apply it here. There is an issue, which is the compressed oracle technique only works for distributions, for your message distributions that are efficiently sampleable. Why? Okay, it is on the compressed oracle technique. The technique itself is only efficient when your distributions are efficiently sampleable. Now, everything we are doing here is efficient, but in order to sample from these distributions, we are using previously cloned quantum states, or maybe this advice state. And turns out that this means that the standard compressed oracle doesn't work. We need to develop an extension where now you can even use distributions that use quantum states as advice. You need many more advice states now, because now your simulated oracle, like you're pretending to be classical, you're only inverse Pauli indistinguishable from classical. And it is inverse Pauli in the number of copies of advice you have. So you need many, many copies to get this really small. However, you can get many copies. Just from our hardness assumptions, we have nice amplification results, even if a state is hard to, if it is easy to clone to some closeness, it's easy to clone exactly. You can show things like that. This technique we think is also independently useful. I know in the past, like for one of my papers, it can be used to massively simplify one of the proofs. I didn't have this technique yet, so we did it the hard way. But if I was doing it now, I could really simplify it, and hopefully can use it in other places. So
just to quickly ask was, sure. Go ahead, Alex. I'll ask after.
No, sorry, I had like a more basic question, because I think I missed this part. So what is the exact classical oracle that you have from the very beginning? Because you were mentioning like this transition from classical to quantum, but I think I missed the exact oracle that,
So here's a Q star that we described. And like I have been in my explanation just saying, once you get these two transcripts, you're done. You just produce two transcripts. But really, that is not the guarantee we have on R. That's just, okay, that's how rewinding usually works. So the guarantee we have on R is if you give it a classical algorithm, it works. Maybe it's doing things that are not rewinding. Like, how do you know rewinding is the only thing you can do? So the way the proof works is you construct this Q star that you're pretty sure, okay, now you should be able to do everything that R can. So you should be like, R should be able to do everything it does usually with the classical adversary, but right now there's no guarantee that why will R work with Q star. So the way you do it is you say there exists some classical algorithm A, which number one breaks the proofs of quantumness. Unbounded time classical algorithm. This is all A is going to basically brute force everything, but it's going to be unbounded time. It's going to break the proof of quantumness. What that means is that R can use A to solve the underlying problem, break the underlying C. And what you will then show is R cannot tell whether it's interacting with this unbounded classical algorithm or this efficient stateful Q star.
Right.
So that is how the actual proof logic goes. So
Yeah.
the first step is going to be fine when even with quantum queries. The second step, that R interacting with A star and R interacting with your classical algorithm A and R interacting with Q star, that these two are indistinguishable. Basically, the way you can think of it is R has another, when R is making quantum queries, it can do things that are not just rewinding. Potentially, like we cannot like just conceptually rule it out. I don't know how to use that, but seems like you can do things that are not just rewinding, because you can do these quantum queries, and then if you're being silly about how you're doing your internal things, you can yeah, if you're silly, then R will be able to detect your quantum and stop working. So that is where the indistinguishability part comes in. And
so all of this, just to make sure that I'm following. So all of this is so that we can talk about quantum reductions, right? For classical reductions, it's much cleaner, like what you already described.
Yes, for classical reductions, what I've said on the screen is basically fine. Like you still need to do the indistinguishability argument, but it's like almost trivial. Like A exactly mimics Q star. And okay, if Q star has some error, then there'll be some error in how close they are. Like if your clones are not exact, then Q star and A are not going to be exactly close, but
yeah,
small error.
I can maybe explain the part I got a bit confused, because I was thinking of like this oracle as essentially the thing that like the output would be just like the transcript, so it would essentially reveal you the messages. That's why I wasn't fully sure what it really means to have like quantum query, if the output of this query just refers to like, you know, this message or the other message. So
right.
I think that's the part that I got confused, since we always have like a classical transcript.
Right. So even if so R interacting with the classical algorithm A can still run that algorithm, like take the code, not really the code, but take the gate or whatever, and run it on a superposition of every message. And then you get a superposition of every answer. So even though A is completely classical, R could be making quantum use of it. And that is that is where the quantumness is being introduced.
Okay, good. And just one more question. So if now I think about this A as a function that indeed I can create its proposition. So for like the recording technique, I knew that in general it performs very well when we have like a uniform random function. So like when A would be like uniformly random. But in your case, A could be like any sort of like a more complicated algorithms. It doesn't need to have like a uniform distribution, right? So you need to somehow be able to generalize beyond uniform A, right?
Right. So that is not new. Like people have done it before. They've done it in a fairly complicated way. In our paper, we implicitly show a much simpler way of doing that, but that was known how to do. If your distribution is weird, we can still do it.
Okay, I thought that you can do it as long as you have like some product distribution. No?
Yeah, it still has to be product, no?
Yes. So yeah, it has to be a product distribution, by which we mean that like every time you're querying your classical algorithm and you rewind and query again, it has to like, after rewinding, it can't remember that I was rewound. So that gives you your product structure. And here that is what we're mimicking anyway. So we still have that product structure. The thing is, we just have this advice that we're using every time.
But that brings me to the question. Sorry. Go on. I thought you were done.
No, just related to this, because I thought that you need some more properties, because as far as I knew, like the extension to like this compressed oracle, when you at least have some sort of like product distribution on every point, so meaning that, you know, the point on the value of x1 and the value on x2 should still not be correlated. But in the case of A, you can still have this correlation between different messages if you want to run, right? So
right. So one way to think about it is the oracle is you're going to send as input the transcript so far, and the oracle is going to give you the next message. Now,
okay, I see.
Because the input contains the transcript so far, you can, for every different transcript, sample independently what the next message is, and whatever correlations are between them will be given by like the input message. So maybe if the input message if the transcript began with 0, all your messages have to begin with 0. But that's fine. That's still like an independent sample from transcript beginning from 1. All your messages have to start from 1.
Okay, I see. This makes sense. Okay.
Right. Yeah. So really the problem is the quantum states here, because in essence you need to be able to map like ket 0 to some to a state which represents your distribution. Like if you measure the state, you get the distribution, and then later on you need to be able to identify this distribution state and map it back to ket 0. Now, if instead of ket 0 you're starting with some psi, you can do this forward map. But like going backwards, you can't necessarily always recognize that, look, this is exactly the state I want, because you could only construct the state using advice. To recognize it again, you need more advice, and that like causes problems in the argument. It just gets a lot messier.
I see.
Okay, and if the advice was classical, is it immediate? How you would generalize it? Or
if the advice was classical,
maybe it's already known, actually. I don't know, but I was just curious.
I'm trying to understand what that means. If the advice was classical,
like maybe think of it as what I'm thinking is that if you have random oracle and you have some advice on the random oracle, so for a random oracle we can run the recording, this the compressed oracle, but conditioned on some I don't know, classical advice on the random function, can we still run it somehow? Or I don't know if it's making sense, right? Like a dumb thing would be like, I don't know, the function has 0 in the first bit or the first response, whatever. So then of course one can, the first one can keep as 0, everything else is like the usual thing, but in general it's not immediate to me. And I'm guessing what you're doing would be a special case, right? Whatever work you have, it would probably also work for a classical advice, right?
Yeah. So with the classical with classical advice, I think the problem just goes away, because you can map ket 0 to your measurement output. Just think of the advice as part of your mapping circuit. I'm not being very clear. Like
okay, I'll ask you later. Yeah, this is like technical stuff as well. Let you continue.
I'll have to think about it. But yeah, okay, this result definitely shows that you can deal with classical advice. I'm wondering, for classical advice, do you even take this hit of number of copies? You probably don't. Like intuitively, it's like you have infinite copies, because it's. So I think you can just like you don't need our extension, I think, to deal with classical advice. You can just do some simple things.
Got it. Thank you.
Our recording technique, and this shows that even if you have quantum reductions for these kinds of protocols, these are the limitations you get. I do want to talk a little bit. So I am like 1 hour is up. I don't know whether the remaining half are supposed to be all questions. I have a bit more. Maybe
no, it's an hour and a half flexible. No, it's an hour and a half flexible. We ask lots of. That's why I was asking you in the beginning if we can ask questions.
Sure. Yes, please. Right. So now I'll come to. Wait, did it move forward? Yeah. Now I'll come to our final results. And here we do actually use the efficiency of the verifier in an interesting way. And what we are trying to answer here is the question of why is public coin proof of quantumness so hard to get? In fact, the only construction of public coin proof of quantumness, and it's public coin asterisk, not exactly public coin. The only construction we know comes from one-shot signatures. So it uses strong forms of unclonability. This is a primitive we just constructed like last year. Best paper at Crypto was about constructing one-shot signatures. And that is the only construction. And even that doesn't get us full public coin. It gets us good enough for our applications, kind of. Still murky, but it requires these heavy assumptions. Essentially, we don't know how to get it from lattices or any post-quantum assumption that we actually believe in. So why is that? Well, we have some explanation. So suppose you have public coin black box proofs of quantumness, here only with classical reductions. Then 4-message versions will imply some variant of quantum lightning. So again, strong forms of unclonability that we don't know how to build. And even if you have constant messages, like more than 4 messages, this implies, again, a variant of public key quantum money. So again, strong forms of unclonability that we don't know how to build. We only know how to build these with IO, and we don't know how to build post-quantum IO. So that is why these are still challenging in some sense, that really we showed that you need some kind of unclonability, but here we need this strong verifiable kind of unclonability if you want to get public coin proofs of quantumness. Or you need a quantum reduction, although I don't really believe quantum reductions can solve the problem. It's just I think we don't have the techniques to show the lower bound. I don't think even with quantum reductions you can get past this. Yeah, a lot of caveats on this, but even on the second thing, the caveat is that we need this quantum info theory conjecture. It's called an LOCC definity conjecture. I don't know if this is true. It's not really my area. I asked some people who do work on it, like I asked Adam Harrow and other people and they said, look, we don't know how to prove it. It seems really hard. We've been working on it, but I would believe it's true. So I am not, myself, I'm not staking any claim on whether the conjecture is true, just that to do it, you would need to violate that conjecture. So another barrier.
And what is the conjecture? Is it easy to understand intuitively?
Oh, I think I don't have it in the slides. Oh no, wait, I have it in my bonus
it's
slides.
okay. I don't want to interrupt you. You only have so many minutes here. Please carry on, and we can do it.
Okay, I'll just give you a high-level idea of the conjecture. What the conjecture is saying is, if you have a bunch of quantum states, they're going to look entangled. But suppose right. Suppose you just permute them, like you have lots of registers, and then you just permute all of them, and now you look at a subset. So do they look entangled, or do they just look like there are some classical correlations? If you have exponentially many registers, we know they don't look entangled. If you have only polynomially many registers, but the way you are looking at these registers is you choose one register, perform some measurement, and then you choose a different register, perform a measurement, choose a different register, perform a measurement. You don't come back to a register you already just measured. Even then, we know that they're indistinguishable. The thing the thing we need is, what if you did a measurement and then you came back? Like, you're not doing any quantum operations that are between these registers. You're still doing measurement and looking at its classical value. So it's still the measurements are LOCC. So they're all classical communication and local quantum operations, but you're allowed to come back. And this apparently is an open problem showing that the definity theorem holds for this setting.
And sorry, just to check one quick thing. So you mentioned, so yes, like the POQ from one-shot signatures does satisfy this, right? Or is there like an issue apart from the strong assumptions that they require? Like, it is a public coin black box POQ.
It is not. It is not a public coin black box proof for quantumness, because the first message, the verifier message, is very structured. It is the obfuscation of certain obfuscation of certain circuits. Although I think that even that kind of public coin, like where the first message is allowed to be structured, but later messages are unstructured, I think even that will get you the same results. I didn't try because I hadn't realized that.
Sorry. I think there's some delay, so I'm talking over it. Sorry about that.
Sure. I was just saying that when we wrote this paper, I hadn't realized that one-shot signatures, the construction you get, the first round is structured. Like, I mean, I knew it, but I didn't I thought, okay, public coin, we get it. But no, it's not really public coin. Only the second verifier message is public coin. So if I had known that, I would have maybe tried to show that, okay, even getting just public coin second message should get you the same results. I'm fairly confident it should all go through.
Right. I was asking this because I remember that in the first paper of one-shot signatures, though, like with the first paper, like from 2020, I think they had like some theorems. They showed that like one-shot signatures implies public coin POQ, And obviously their construction didn't work, but I think like this statement alone was sort of like an independent of how you construct OSS.
So how do you get a proof of quantumness from a one-shot signature? The only construction I know, I don't remember what's in that paper, but the trivial construction that I've been working with in my head at least is you send your public parameters, and the signer is going to send you their public key. Sorry, their verification key. And then you're going to sample a random message and say, hey, sign that. And the reason this is a proof of quantumness is if a classical prover could sign, you could rewind them and get signatures on many strings. And with a one-shot signature, the property is even the signer can only ever sign one string. Now, I don't know how if the first message is okay, I think I know. I think I know what you mean. So I think they're constructed with a CRS. So instead of the verifier sending the first message, they just have a structured CRS. And now the verifiers.
You are exactly right. So they have like a CRS, and then they send like first the public key of the signature, then verifier sends a message, and then the signature. So
yes.
It's like a free message public coin POQ in CRS. The CRS model.
Right.
But
so in R
without any CRS. Yeah.
Or you can generically make the CRS the first verifier message because the verifier is always honest here. So unless the CRS is inefficient, which is kind of crazy, but if the CRS is efficient, the verifier can just generate it. So it does fit into 4 rounds. The meaning of public coin becomes like slightly different, where in their setting, they have defined public coin to not include the first message.
Okay, makes sense.
Okay. So one thing I want to talk about here is what I mean by a variant of. Because here it's not those pesky adjectives from before. It's like a meaningful difference here. So I want to cover quickly what is a quantum money mini scheme. This is what I refer to as public key quantum money effectively. And this is going to be a sampler which samples a classical serial number S and a quantum banknote $S. So anyone can sample serial key and banknote. And the verifier is going to say, for this given serial key, is this banknote valid? Now, the security property here, security property here is that, first of all, correctness. If you sample the banknote honestly along with the serial key, it is going to verify and accept. And security is that given the banknote sampled from the sampler, it is hard to compute some state rho AB where both row A and row B are going to verify. So it's effectively 2 banknotes. Could be some weird entangled state, but as long as each register independently passes verification. So our weakening, the one we obtain, is here we say that, okay, you can sample a banknote, but the security property is that given one banknote, it is hard to come up with n banknotes. Maybe it is easy to come up with 3 banknotes or like root n banknotes. But there's a known polynomial n where coming up with that many banknotes is hard. Now, interesting question. Do these weakened mini schemes, what is their relationship with full mini schemes? We don't know. We thought about it. We thought it seemed hard to show any show either that they can be used to build mini schemes or that they cannot be used to build mini schemes. However, these don't seem any easier to build, at least from the techniques that we know. And it seems like if you have to build these, you might as well be building like proper mini schemes. So there still seem to be a fairly formidable barrier to getting public coin proofs of quantumness. So this is a weakening for, so variant of quantum lightning is going to be this kind of cloning hardness. We're getting many. And why you need many is going to be because a reduction can be rewinding many times. So you need many clones. If your reduction only rewinds twice, then you only need 2 clones. And likewise. In fact, even constant time, even if your reduction is only rewinding constant number of times, that still gives you full mini schemes. It's only for these hypothetical reductions that are rewinding many, many times that is the problem. Okay, so I'll just quickly look at what is the basic idea here again. It's just going to be conceptually a slight extension, but the technical content is much more involved in the proof I showed. So the question is, can you use this hard to clone state? So already in our proof of quantumness, we established that there's this state which is hard to clone. So is this our quantum money scheme? Like, is this can you just say that given the transcript and this state, you can't clone the state? So the issue is that while it is true that this state is hard to clone, for quantum money, we don't just need states that are hard to clone. We need states that are hard to clone but easy to verify. In particular, you could come up with clones that are completely different from each other, statistically far, but maybe they fool the verifier. So let's see why that comes up. So the claim is that the state is hard to clone. So what is our verification circuit? Like a very natural thing to try. How do you verify that this is the state you got? Is just run the rest of the protocol using this state. So this state is supposed to be the internal state at some point in execution of the protocol. Just run the rest of it and see, does it accept or does it reject? And you can use this verification procedure and you start getting some things, but you face some like fairly steep challenges. First of all, your notion of cloning is different. So clones may not be indistinguishable. Now recall that your reduction is not going to be a verifier that looks at just one state. It is going to be running it's going to be rewinding many times, using them to generate many transcripts. And maybe one transcript alone looks like it verifies. But many transcripts together could start having correlations amongst them in the reduction. Say, hey, I expected independent samples, but these are actually always like different always correlated in some way. So that is a problem. Before you even get to that point, you hit the problem that suppose you have a long protocol with many rounds. So after each round, you need to be making clones. So you make clones and then use that clone to do the next round and get some residual state. Again, you need to clone that state because every round is a site where the reduction can rewind. So what you need to do is you need to produce clones of the state, measure them, and then clone the residual state again. While what kind of hardness does this give you? Well, the problem is if you have an adversary which is winning your cloning game of clone this internal state, the clones it gets could be completely different from the original state, and therefore there is no guarantee that they can be used again to get more clones in the future. This is a little bit vague. I have a diagram somewhere. Yeah, and bonus slides. Right. So we have this first run where you clone to get the state psi. Where you first get the state psi, honestly, you clone it to get two registers row A, row B. And then when reduction is going to ask for another rewinding at this point. And now this row A that you got, this adversary is telling you it can clone honest states. It doesn't say it can clone these malicious states which have been generated by a different adversary. And the way you resolve this is you do some bootstrapping. You use the old adversary to define a new cloning scheme. Like now you'll say row A is hard to clone. And then either it is hard to clone, in which case you're done, or you get an adversary which is cloning it, and then you can clone row A as well, and you do this. And this like recursive use of adversaries is why we get stuck at constant rounds, where we cannot go more than polynomial. This is the main issue, because we have to do this repeated bootstrapping. Yeah. Now the second problem is, even if you don't have this issue of repeated cloning, you're cloning just fine, because your verification check is only looking at one state at a time. It could be the case that your states individually all pass verification, but have some strong correlations between them. So your two clones, for example, one always starts with get 0, the other always starts with get 1. Now, if you just look at one of them, it looks like you randomly chose 0 or 1. But if you look at the other, it has this strange correlation. Like, okay, when you look at both, you say, okay, these are not honestly sample states. Now, this is for classical correlations. There are ways to deal with it. But really, the problem is that these states could have quantum correlations. So in the worst case, you can construct an example where a reduction is going to rewind, and each state and your cloner, which is passing all your verification checks, is getting this large entangled state, and then the reduction by asking measure the first state, and then later on saying measure the second state, forces you to run a non-local game, and just from your classical outputs, prove that you are actually quantum and you're not a classical algorithm. I think this also I have in my bonus slides. Yeah, sorry, this part of the talk is not structured completely. But I rarely get the time to get into this stuff. Yeah, so a bit of a dense slide. But suppose, for example, you had, suppose your game was just prepare state ket plus and then measure it in like some basis. Like you're in the first message going after the first message, you're going to have the state ket plus, and then you in the later messages, the reduction is just going to say measure it in some basis and tell you what the basis is. So now your verification check is this: that does your state look like ket plus, or maybe the verifier just says it always accepts for everything. Then what a cloner could be doing is it could be taking this ket plus and giving you a clone that is EPR, and verifier, because verifier always accepts, is going to accept both halves. And now what is happening is R can say measure one half of the EPR in M3 saying measure in this basis, in M3 prime saying measure in that basis, and get correlations which are running the CHSH game. This isn't very, I've not been very clear here. But quantum correlations are a big problem because quantum correlations can prove that you're not running separate classical adversary every time. You are just running some Q on an entangled system. It can be used to detect this kind of entanglement, which never arises in the classical case. And this is where we need the LOCC definity entangler. When you have 4 rounds, we know such an disentangler exists. You just shuffle, you get many copies and you shuffle them all. And now a small subset, just we can show you cannot do any non-local shenanigans. It's just a small subset. When you have many rounds, then it becomes more complicated and you need this extension. Right. I will just have one open problem slide and then everyone can go home. So there are many open problems. So there are all open problems around the mini scheme stuff, like the weak mini scheme. We know if you are making constant mini clones, if it's hard to make constant mini clones, we can amplify to get full mini schemes. What about more? But okay, here are some open problems that I've not mentioned. So first of all, the generic bounds that we showed, result 1, which was breaking into either everything collapses to 2 rounds or it requires cryptography. That only holds for constant many rounds. Can we show some generic bounds for polynomial round proofs of quantumness? It seems really hard because of some issues I mentioned earlier. And our techniques only get us constant rounds because of similar bootstrapping kind of issues. And the second question, I hinted at this, that there is, it seems that IO and all, the reason they cannot be used to build constant round proofs of quantumness is because of this requirement of collision resistance. And all our constant round constructions do have collision resistance in them because they're using trapdoor claw-free functions. So can you make this like formal? Can you say it requires some form of collision resistance, or it requires statistically hiding commitments, which I think is going to be the right object to get? That seems very close. Like seems like you have the like all our techniques are using these things. Can you show it formally? Finally, the stronger bounds I showed for where we are actually using the efficiency of the verifier, they're all for public coin proof of quantumness. The reason is not that the technique stopped working for private coin. The reason is that the objects we get are much weirder. So here we are getting primitives which are like quantum money. There's publicly verifiable. There you get some kind of privately verifiable quantum money. So if I just state it like that, privately verifiable quantum money, you just get from BB84. But here you are getting something that is non-trivial. We just don't know the right way to describe it. So can we get like better bounds for just using the verifier, just for a private coin black box proofs of quantumness? Can use the verifier in some interesting way. Finally, the thing I mentioned, can you amplify weak quantum money? Can you show you cannot amplify weak quantum money? There have been some recent results on QMA versus QCMA. I feel like maybe they should be helpful because we are running into similar problems when trying to show barriers. So maybe you can like show that you cannot amplify. Okay.
Can I ask a quick question about question 2?
Yes.
So for this one, how would one can approach this kind of question? Because as far as I know, the only way I'm aware that people show that impossibility from something weaker than collision resistance would maybe to try to show that, okay, in some, let's say maybe like random oracle model, you cannot show that maybe like random oracle suffices. But for POQ, we actually know that random oracle would suffice. So if you really want to show that you cannot do it with like something weaker than collision resistance, do we have any approaches or techniques for showing this kind of stuff?
So when you say random oracle suffices, so first of all, random oracle does give you collision resistance, so that wouldn't be enough anyway. But the way our proof, the way our proof works is I give you like random oracle and the second oracle collision breaker, and this second oracle is going to break all collision resistant constructions, even ones that use O. And in this world, we show that proof of quantumness cannot exist, even though all these other primitives exist. And our construction is an extension of these techniques to an interactive setting. And here we say, along with random oracle, I even give you an IO oracle, and even then you can't. So showing a barrier, I feel like we've mostly done it. The more interesting direction for me is start with, say, a statistically hiding commitment, and you know nothing else about it. Can you use this to construct proof of quantumness? Or actually, no, that's not what I'm saying, right? No, I'm saying that yeah, start at the proof of quantumness, and you know that, yeah, start with the proof of quantumness. You know nothing about it except that it is interactive in some way. So that is part of the trick. You have to define what it means to be interactive. Like maybe you can use the fact that this black box reduction exists. And then using these techniques, again, you try to get a statistically hiding commitment is what I feel would be the.
So you want to claim that an interactive or like, let's say a 4-message POQ would imply a statistically hiding commitment, I think.
Yes, yes. That would be the concrete thing that I believe should be true, but I don't know if it is possible to show, at least with the techniques we have so far.
Yeah, and indeed it would answer this question that you mentioned here, this question, I think. Sounds good. Thank you.
Sure. That is all I have from my side.